In this video, we're computing the integral of sine x times sinch x, where sinch x is the hyperbolic sine of x. Now, if you haven't seen a hyperbolic sine or hyperbolic cosine before, I'll post a link at the top to my main video on the sinch function, the cosh function, and their derivatives. But just as an extremely compact review, the sinch and cosh functions are defined in terms of exponentials like this. There's the sinch function, it's 1/2 times the quantity e to the x minus e to the negative x, and the cosh function 1/2 e to the x plus e to the negative x. And it's quick to see that these two functions are equal to each other's derivatives. So the derivative of sinch is cosh, and the derivative of cosh is sinch. And you can just take the derivatives of these exponential expressions to prove that to yourself. So the point in this integral is that we're going to stay in this sinch and cosh notation. We're not going to expand into a bunch of exponential functions. And we just use the fact that the derivative of each of these functions is equal to the other one. And so that's true for their antiderivatives as well. So back to the integral, like how are we going to attack this thing? Well, this is an integral of a product of two functions. And for that, we use integration by parts. And this falls into the trickiest class of integration by parts problems because neither one of these functions gets inherently simpler when I differentiate it. Both of these have a kind of looping structure to them. When I differentiate the sine, I get the cosine. When I differentiate the cosine, I end up with the negative of the sine. And then sinch has the same kind of looping thing, except without the minus sign. So if you differentiate sinch, you get cosh. Differentiate cosh, you get sinch. So this is the case where we can't use integration by parts to sort of chip down the complexity of the integrand until we get to something simple enough to compute a final integral. In fact, we have to use what I've called the looping trick. And I'll post a link to the video at the top where I first introduced the looping trick for integration by parts. So what we have to do here is repeatedly apply integration by parts, and then we're going to look for a copy of our original integral after two applications of integration by parts, and we'll be able to move that to the left side of the equation and isolate it. So one key point here is as we're repeatedly applying integration by parts, once we choose our u, and I'm going to choose sine x for the u, we have to define u with that same piece of the integrand on the second iteration. So you'll see exactly what I mean in just a second. So on our first iteration, I'm going to define u to be sine x, and then dv, that's going to be sinch x dx. So we get started with integration by parts here, and I want to make my substitutions very clear. So let u equal sine x, and that means du is cosine x dx. And then the differential piece, dv, again, is going to be sinch x times dx, which means v is the antiderivative of that function, and that's cosh x. Again, because sinch and cosh are just equal to each other's derivatives, so the same is true for their antiderivatives. So we apply the integration by parts formula, and we have our original integral, that's sine x sinch x dx, is going to be equal to u times v, that's sine x cosh x, minus the integral of v times du. So I have cosine x cosh x dx. So at first you might say, well, we haven't made any progress here because the integral that I just produced is just as complex as the one I started with. But again, the idea is to apply integration by parts again and choose the same piece of this integrand as your u. In other words, we're going to take that cosine piece and let that be u, and that'll end up being differentiated again. So this time we say let u equal cosine x, and that means du is the negative of sine x dx, and dv is the other part of the integrand, that's cosh x dx, which means v is the antiderivative of that, or sinch x. And I'm going to keep the left-hand side here to highlight the looping trick at the end. So we're looking at modifications of this original integral, sine x sinch x dx. And what we have so far is that it's sine x times cosh x, and then minus this integral of cosine x cosh x, which we're now applying integration by parts to. So when I do that integral, I get u times v, or cosine x times sinch x, minus the integral of v du, but du has a minus sign on it. So I can pull that out in front, and I end up with plus this next integral, and that's going to be sine x sinch x. So we can distribute the minus sign across these brackets. And on the right-hand side, I end up with sine x cosh x minus cosine x sinch x, kind of a nice symmetry to this, minus the integral of sine x, sinch x, dx. And what I notice is on the right-hand side, I have the negative of the original integral that we started with. So we're trying to compute the integral of sine x, sinch x. And here's another copy of it over here with a minus sign in front of it. So what I do is add that to both sides of the equation. The left side is the original integral, and on the right side is a negative of the original integral. So let's add that to both sides. That leaves me with twice the original integral sitting on the left-hand side. And on the right-hand side, I have a sine x, cosh x, minus cosine x, sinch x. Now all we have to do is divide by 2, and we've isolated the integral that we were trying to find. So I have the integral of sine x, sinch x, dx turns out to be 1/2 times sine x cosh x minus cosine x sinch x. And because this was an indefinite integral, at this point I should throw in a plus c. Now if that trick seems too wild to be true, you can always take this expression and differentiate it. You're going to have to use the product rule on each of those terms, and a bunch of things should cancel, and it should simplify to sine x sinch x. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.